Hello Year 9 and welcome to our fourth week of distance learning. We are looking at this topic before. We've spent a lot of time now looking at all of those different limiting factors of photosynthesis. Today we've got a bit of a summary of that. We're also going to look at something called the inverse square law. We're going to look at how we analyse data on graphs as well. So let's get started. So we first of all, now this is up to you, okay, because if you've got good notes in your book for each of those limiting factors, then actually you probably don't need to summarise this. But if you want to, you can pause this slide and you've just got that summary page of each of the ideas that we've talked about. So we've said that this is a required practical. The required practical states that we're looking at light as a limiting factor, but as we know, we can see lots of different examples of exam questions. We have looked at light as a limiting factor, carbon dioxide in the form of that sodium bicarbonate, temperature, and we haven't talked about chlorophyll yet, but we have referred to chlorophyll as being kind of like an oven. So we've got our reactants, that's like our cake mix, and the more chlorophyll, the more ovens we've got, the more photosynthesis can occur. So you can see the more chlorophyll always means a higher rate of photosynthesis. And you can see I've got these pink sections where you can see that is where that is a limiting factor. So when light has reached its optimum or gone to a higher light intensity beyond its optimum, something else is a limiting factor. It's no longer the light, okay? And the same for all of them. So when the temperature is not at its optimum, it is a limiting factor. When the temperature is at its optimum, something else has to be limiting that rate of photosynthesis. And we can keep repeating testing, okay, and I'll talk about that a bit more in a minute because we will see that from our graph analysis. A little bit tricky to get our head around, but we'll give it our best go. So we can see here that we've got our, this is called a sketch graph. It's a sketch graph because it's got no numbers on it, it's just giving us a pattern of results. Because the numbers could depend on how much pondweed we used, various other factors, whereas this tells us however you do your experiment, so long as you've just got that one independent variable, you will get this pattern of graph in your results. So light is a limiting factor affecting the rate of photosynthesis up to the optimum. After the optimum, there is no benefit to increasing light and it costs more, okay? It all comes down to cost. We're trying to maximise plant growth, maximise photosynthesis without spending lots of money in doing that. Same conversation for carbon dioxide. You can see it's the same shape graph. So carbon dioxide is a limiting factor affecting the rate of photosynthesis up to the optimum. After the optimum, there is no benefit to increasing carbon dioxide and it costs more. So we've seen the same shape in the curve there, and we've seen that they both get to that optimum and then level out. And don't forget, we counted, or we kind of were able to measure the rate of photosynthesis by looking at the amount of oxygen produced, and then we could relate that to rate of photosynthesis, and we can also calculate that as a rate, which we will look at in another time. We'll look at it in one of the other required practicals, showing how we can calculate rate. Okay, it's done slightly differently in biology to how it is done in chemistry. And then we've got temperature is a limiting factor before and after the optimum, as enzymes work best at the optimum. Now, if we haven't done, well, my class or the classes that this is aimed at, we haven't done B2 yet, so we don't know a lot about enzymes, but enzymes are present in the human body. That's why they work best at our body temperature, which is 37 degrees C. And if we get too hot, then enzymes start to change shape. We call that denaturing. Happens exactly the same in the plant. So we don't want the temperature to get too high because those enzymes will stop functioning. And then chlorophyll is always a limiting factor. The more chlorophyll will always result in a high rate of photosynthesis. Chlorophyll is limited in variegated leaves. And we've talked about those before. Those are the leaves that have got the white or yellow patches on them, a bit like a spider plant or a geranium, and there's no chlorophyll in those sections, therefore no photosynthesis taking place in those parts of the leaf. And we used this program just at the bottom left there, and we monitored the rate of photosynthesis by looking at the oxygen produced. So that's kind of our summary. If you do feel that you want to do some quick sketch graphs, maybe take one page in your book and do like a summary page, then absolutely go for it. If not, you might want to just do the chlorophyll graph, because we didn't investigate that one using our computer model. Okay, let's move on. If you need to pause, pause now. Okay, we're now going to look at a 6-mark exam question, just to show you really how we can investigate all of these different factors, and then we get into the exam and they give us something totally different, okay? And this is a real exam question that we're going to have a go at for 6 minutes and see if we can answer. So it says the rate of photosynthesis in pondweed, that's familiar to us, we've looked at photosynthesis in pondweed, is affected by different colours of light. So that's something that we've not come across before, okay? So we've looked at light intensity, temperature, etc., but we haven't looked at colour of light. Describe a method you could use to investigate this. You should include what you would measure and the variables you would control. So this time maybe we've got some coloured filters we can put in front of the lamp, but we're going to use different colours of light, but we're going to use the same principle of the same method that we used before, okay? So we're going to have a go at doing this now. Don't just skip forward and copy out the answer, okay? So give it your best go. 6 minutes, 6 marks. You need to pause it so that you can have a good go at that question, okay? And pause now. Okay, let's have a look at the mark scheme then. So it says here that the kind of blurb at the top just basically says in order to get 5 to 6 marks, you have to have a coherent method. It needs to have the relevant detail which allows someone to actually follow that method and get valid results. Now, valid results takes into account the equipment we've used. Have we just got one independent variable? Have we got repeats in there to make it reliable? All those kinds of things, okay? So we talk about how and we're doing our green pen now. Is my green pen icon getting hot? There it is. We talk about how the apparatus is set up. So we've got our pondweed submerged in water. You might have a beaker of water there so that it doesn't overheat. So that's this one here, reference to control of temperature. You've probably then talked about how you're going to use a filter in front of the light. Always keep the light at the same distance, and then allow it to acclimatise. We talked about that before. Allow it to kind of get used to the new condition and the plant to kind of acclimatise is the best word. I'm going to use the word adapt if you're not sure about acclimatise. So it's kind of getting itself to the photosynthesis level with that coloured filter. And then maybe for, give yourself some kind of time scale. So maybe for 10 minutes you're going to look at how much gas is produced, how much oxygen is produced, or you could say that you're going to count the bubbles of oxygen for a minute or something like that, and you can see those points here. Same length of time each time, so that helps you with one of your controls. You're not going to change temperature, you're not going to change the carbon dioxide, and then you're going to repeat the experiment with different coloured filters. So you might suggest some colours. You might say you're going to use a green, a red, a blue, a yellow, whatever you want to use. You could suggest some different colours of filter. And then at the end it says to do some repeats and to calculate a mean, okay? So we've got quite a few bits of information there. The only real difference there was the coloured filters, okay? So everything else we were kind of comfortable with from the previous work we've done. But then adding the coloured filters was something that was a bit new, trying to take us out of our comfort zone, but hopefully we stayed right in there and were able to tackle that question. Now, because coloured filters are, we would describe that as discrete data, okay, so continuous is where we've got different light intensities and we've got number values to that. This is discrete data or discontinuous data. It's or even you can call it categoric data, okay, because it's categories, it's the blue category. We would use a bar chart for this, so we would have all of our different colours and we would do that as a bar chart for how much gas was produced for each coloured filter. Okay, and you could even put them in the order of wavelength if you look those up. Basically the spectrum of light in a rainbow, which is quite topical at the moment. You could put that into order. Okay, so that's that question. Hopefully you've had enough time to do some green penning. If you still need extra time, then pause now. Okay, so we're actually just starting the lesson. It's not a huge lesson, don't panic, don't think we're going to be here all day. I know we spent 10 minutes already having a look at some stuff to review from last lesson, but we're moving on to this last part of this section now. So what are the best conditions for photosynthesis? That is our title. Let's write that down, please. After this lesson, we're going to be looking at what the plant does with that glucose that's made in photosynthesis, but for today we're just going to continue finishing off what we're doing with the required practical there. So what are the best conditions for photosynthesis? Get the date written in your book as well. Okay, this is week 4 of distance learning and week 6 of lockdown. Okay. So, application of investigation data to maximise profit for farmers. That sounds all a bit technical, doesn't it? All I really want you to do is just identify from your graphs what were the best conditions. So what were your optimum values for each of your graphs that you produced? Okay, so they were, I can't go back to mine because I'd have to flick through lots of slides, but what was the best condition in terms of light, what was the light intensity that was needed? I've got a feeling it was 50 lux. What was the best temperature, and what was the best sodium bicarbonate percentage to use? And then the final one is just maximum chlorophyll, because the more ovens you've got, the more baking you can do. Okay, and to justify those conditions, really what I'm talking about here is just, why would we want to do that? Okay, justify means give a reason. Okay, so you could say, well, I don't want you crossing the road without looking. Okay, well, justify the reason, because there might be a car coming. That's what we mean by justify. Okay, so giving a reason why we would want those conditions for farmers to maximise profit. And that's because if we increase those factors beyond where they need to be, beyond the optimum, and it makes no difference to profit, then it's just wasting money in setting those situations up. And there's just a note there at the bottom that says carbon dioxide in the air is only about 0.04%. It's actually 0.035, so it's even less than that, but to 2 decimal places it's 0.04. However, commercial greenhouses, so this is where they grow food for the supermarkets, they increase the carbon dioxide to about 0.1% because they know from these investigations that it helps to maximise photosynthesis and maximise profit and growth. Okay, if you need extra time on this slide, pause now. Okay, now this is higher only, so if you find this a bit hard to get your head around, that's absolutely fine. Okay, we've got a couple of slides left, and then we're at the end of today's lesson. So we're looking at more than one limiting factor on one graph. So we've got carbon dioxide, we've got temperature, and we've got light intensity. Now, go with me on this, okay? You might have to listen to this twice. So basically, I've taken my pondweed, and the first thing I look at, okay, forget what we've done in the past, but the first thing I look at is light intensity. And I do this investigation here at the bottom, okay? So I've got carbon dioxide at 0.03%, and I'm using 15 degrees C. And I increase my light intensity, and I find that the best light intensity is this one here, okay? Not very far along, along the bar there, okay? Oh, didn't want to do that. Okay, you can see it's just here using the mouse, and it hasn't really, increasing light intensity hasn't really had a massive impact, okay? And then what I do is I decide, right, okay, the next variable I'm going to do is I'm going to increase the carbon dioxide to 4%, still keeping my temperature at 15. And so that is this line here. Now, if I just had started off and said, right, okay, from my first investigation, I know that light intensity, the optimum is just about here, and then I increase that carbon dioxide and I've kept my light intensity optimum, I find that the best condition for carbon dioxide at 4% is about here. Whereas in reality, if I then retest at 4% carbon dioxide light intensity, I find that that optimum has shifted all the way from here for light intensity to up here. Okay, and then I increase the temperature, and actually it's quite similar. Okay, the optimum for light. What I'm trying to say is we can go through and think we're getting our optimum conditions, and then we actually retest our first variable and find that we can just tweak it, just improve a little bit further. Okay, so if I just kept that information and gone, okay, well, here is light intensity at this low value, I'll always keep my light intensity here, and then we work out up here that if we increase carbon dioxide, it increases massively. If we just kept that same safe light intensity, we would never know about this massive increase in rate of photosynthesis up here. So it's about repeating our tests, tweaking it, getting it to the best possible conditions we actually can. Okay, so that's analysing graph with more than one limiting factor. Our ultimate conditions are 4% carbon dioxide, 25 degrees C, and a light intensity kind of at about 2/3 of the way along the scale there. If you need extra time on this slide, then pause now. If you find that difficult, then don't panic too much because it is higher content. Okay, last slide then. This is called the inverse square law, maybe second to last slide, sorry. This is called the inverse square law, and basically it's saying, if I move a lamp twice the distance away, okay, if I square 2, because I've moved it twice the distance away, that's 4, the light intensity is 4 times less bright. Okay, if I move the lamp, and the reason why this grid is here is to really just help with our times tables, our squaring of numbers. If I move the lamp 3 times the distance away, the brightness of that lamp is 9 times less bright, okay, because 3 times 3 is 9. Okay, so the question says, if the lamp is moved 6 times as far away, how much will the light intensity decrease? So it's moving 6 times the distance away, so 6 squared is how much less bright that light will be. Okay, and we call this the inverse square law. So here we're moving it 6 times the distance away, and 6 squared is 36. So the answer to this question here is the lamp will be 36 times less bright than it previously was. Okay, just something to try and get your head around. It's probably going to be a quick 1 marker somewhere. Say something like, you know, a lamp is moved 7 times the distance away. How much less bright is it? And so 7 squared, 49 times less bright. Okay, so it's just about knowing how to square numbers, which I'm pretty sure we can probably do. Okie dokie. If you need extra time on that slide, maybe write some notes, then pause now. So here we are, we're looking at it again. So we've got another example. This is how it will look in an exam, and it's a bit scary. I've tried to do the easier version. Okay, so if we take the light intensity at 10 centimetres away, okay, and we've just got 1 over the distance squared, it gives us a value of the light intensity in arbitrary units. We then take the distance 20 centimetres away, okay, so it is it's kind of increased the distance again by the same amount, and we've got 1 over 20 squared. It gives us this value of light intensity in arbitrary units. Okay, again, let's write some notes from this slide. We're nearly done. Okay, if you need extra time, then pause now. And that's the end of our lesson. So, hope you liked it. I think probably at the end it got a little bit confusing. Hopefully we will, if we need to revisit that, then we can. But basically, the best way I can say is to use that idea of however many times further it's moved away, square that number and it's that times less bright. So you've been watching my YouTube. If you could subscribe, then you will see when I put up new videos, loads and loads of content in there for other topics that we've done. B1 is in there if you want to do some revision there, or if you just want to look at some other videos. There's some fun stuff in there as well, heart dissection and the thermit reaction and stuff like that. So if you're interested, then subscribe, and I hope you have a good day and enjoyed that lesson. Thank you.